I'm going to be going through the fourth chapter of the preliminary engineering studies HSC or Year 11 engineering studies course. This is dedicated to biomedical engineering. I'm going to be going through Paul Copeland's Engineering Studies, the Definitive Guide. So the first thing in the book is about the nature of work done by biomedical engineers. So at the start of the year, I will have gone through some innovations, and I'll go through those now. So I'll revise those now. So at the start of the year, I talk about a variety of engineering innovations. So we'll just have a look at the history of biomedical engineering. So the oldest wheelchairs are about 4,000 years old. So there's depictions from Greece and China that are a little bit older. It seems that widespread use of wheelchairs was probably about 1,000 years after this. Modern wheelchairs, I think, were first developed in the 1930s. But we have prosthetic legs, so you might be familiar with, pirates with peg legs or hooks. These prosthetics replacing body parts there's archaeological evidence to show that that's very old, more than 2,000 years in the case of this prosthetic leg. The stethoscope in 1816 is generally considered to be the start of diagnostic equipment. So the idea that this person here, Rene, I don't know how Lenec, I guess I'd pronounce that last name. Normally doctors would put their ear to a patient's chest. Rene didn't like putting his ear to his female patient's chest, so he came up with a device so that he could listen. And prior to this, really, doctors didn't have a lot of tools that they could use to identify illnesses. The stethoscope was the first thing where, so there's a 99% Invisible that will do podcast that will do a much better job of going through the detail than what I can recall, but they make the claim that this is really where doctors had a diagnostic tool that they could use to help better understand illness. Carbon fiber is a very old engineering material that is older than people would assume. Modern applications didn't really see use until the late 20th century. Stainless steel is an engineering material that we learn about that in this chapter. We also will learn about titanium in this chapter. This image is a 3D printed skull or skull fragment that can be used in surgical replacements. We are going to talk about implants. So implants there's a variety of different implants. Implants could be anything as small as a stent that can keep your arteries open to help keep your blood vessels open to prevent heart attacks and strokes. Whereas probably the most common or definitely the largest implant that we put in, I'm going to say definitely, but I think it's the largest implant, is the hip replacement, and we will talk about this a fair bit. So it's something to look at the different parts of an artificial hip. What we call this is a hip stem. So we don't replace the whole bone. What we're doing is replacing that joint between the hip. The implantable pacemaker, I would have spoken in my previous recording about why we use these, but they regulate your heartbeat to stop you from dying. The sip and puff typewriter, I also spoke about that when we went through these examples last time. I like this as the example of an assistive device to help people with paralysis, and this has led to sip and puff wheelchairs that allow people to have mobility, and so that's why I see also wheelchairs. But these typewriters allowed people who didn't have access to their arms to still be able to communicate, to write a letter or to be able to write things down when no one else was there to help them. The modern evolution of this is that we're starting to look at using brain activity as a way of controlling devices for people who don't have access to their hands. So we then have CT scans. I talked about when I discussed this previously, I said these are really important for detecting stroke. They're also important for finding cancers and the size of cancers, blockages, So these are a pretty big advancement in technology. Optical fiber. We talk about this in there's a video that I use mostly for year 12s for the telecommunications course, where we talk about the video is called Lightspeed, and I show the video there where I talk about optical fiber in great detail. But they do talk about how optical fiber was used for endoscopes, so to be able to see inside people. Yeah. Cochlear implants, we're going to talk about that today, and they're a bionic ear. They allow people who have hearing loss or no hearing at all to have some hearing, not perfect hearing, but it's getting better and better all the time. That's an Australian innovation. It's worth pointing out. So the Jarvik artificial heart is at my old school. I used to talk about this when we did plastics in our lives, because it's a plastic that we need a plastic that's strong but also very flexible and fatigue resistant, because that plastic membrane is going to have to move pretty much once a second, or maybe a little more than once a second for potentially years. The fewer times we have to replace this heart, the better. So it's made out of something called Abicore that we'll learn about later. And that prior to artificial hearts, before having an internal heart, people would have to use a device that lived outside of the body. Anytime you have a connection between the outside of your body and the inside of your body, there's a big risk of infection. But more importantly, prior to this, people had to carry around a fairly bulky device. And I like to use the example of, imagine having to go on a date, and you say, well, look, I'm going on this date, but I need to carry something the size of a mini fridge with me. And that really is the life-changing effect of some biomedical innovations, is that you don't have to say, hey, I'm going on this date, how do you feel about me taking a mini fridge with me? I can't go anywhere with this stairs. And having a totally internal device drastically improves the quality of life for people. We're going to learn about how the first people to receive these implants, that they didn't live a particularly long time, and they were willing to take on that risk to be the trial patients, because their quality of life was pretty poor anyway. Fmris, I spent a long time talking about this when I first talked about this in Engineering Innovations, which should be available. You should be able to find that video. But the idea of Fmri scanners, as a refresher, they allow us to see the relative brain activity. So obviously when you're just existing, you're using brain activity to keep your lungs pumping. There's a whole lot of processes that your body needs brain activity for. But what we can do is we can see that when you start thinking about food or reading or lying, different parts of your brain start demonstrating more electrical, more brain activity. And that electrical activity that is found in the brain can be detected with big magnets. So you have to be careful when you go in an fMRI or even an MRI, that you don't take any metal with you, that it could be magnetic, because that's bad for everyone. And by detecting the relative amount of activity, we can see what part of the brain is activating. This has been a big advancement even in psychology. So this is prior to this, psychology had to be very observational, whereas now we can really see what's going on in the brain and giving us much better understanding of the brain. Okay, and then the last one I have here is sensory feedback. So this is similar to the cochlear implant, but the idea here is that, and we can see this in one of the videos that I'm going to use from Catalyst, that we can now stimulate the nerve endings that we can record the nerve endings that would have been observed. So in the case of the bionic ear, we'll start with that. We can convert sound to an electrical signal. And in your ears have little tiny hairs inside the cochlea, and that when you have hearing loss, those hairs fall down and they won't stand back up. But what we can do is we can simulate the electrical signal that those little hairs would have sent to the brain, and what we can do is we can send those signals to the brain directly by using electrodes, by using pieces of metal that we just plug into the brain. And we can take someone without hearing loss, and we can just take an electrode and stimulate that same area of the brain, and we can make them hear just a loud noise, or we can put into the optical center of the brain and they can start seeing a bright light or colored lights. And in the case of hearing loss, we can actually simulate, we can play back the electrical signal that that part of the brain would have received, and that's how we were able to produce the sound that the person would have heard. Well, we can now do that as well with sensory feedback, so we can now do that with touch. Now, touch is getting much more precise, and this has taken a longer time to produce, but we can record the sensation that someone would have felt, and then we can simulate that and play that back to the brain. The idea is where we could be in perhaps 100 years, is we could get to the point where we will be able to go into a virtual reality setting where we can completely plug into the computer will be able to plug into our brain, and we'll be able to simulate the feeling of being in that virtual reality, as well as the sounds and maybe smells of that environment. And at the moment, this is being used for people with prosthetics. So this, for instance, this man has lost his hand, and he's now got a prosthetic hand, and the sensory feedback that he's getting from the hand, so that he can feel the cup without having any nerve himself in those hands. Okay, so that's my summary of the innovations. What we're going to look through the rest of the book and see what we cover in these notes. So we have the nature and range of work done by biomedical engineers. I'm going to cover that in greater depth, but at the start of the course, I talked about how much effort will that be to find? I'll find it. You might remember me going through this, and for biomedical, which is purple, no blue. Okay, biomedical engineers are responsible for the design and implementation of technologies and treatments for medical conditions. This ranges from artificial limbs, organs, and joints. This also includes implants, scopes, and scanners and monitors. So the first one we have, artificial replacements. Then the next one we have is what I call diagnostics, so things that allow us to understand what's going on. So things like scopes, scanners, and monitors, they help us to know what's happening in the body, to see inside, or to monitor activity. So the machine that goes beep, beep at the hospital. Then the next category is treatment and delivery methods. So treatment and delivery methods, things like radiotherapy. I didn't have that in my slides. Radiotherapy for cancer, so we shoot radiation directly at people. But also we have surgical techniques, so things like laparoscopic surgery, which I'll talk about in a second, and assisted devices. So that's sip and puff typewriter to self-driving wheelchairs, up to assistive robots is another thing. So let's have a look at some of those points that I talked about there. So laparoscope, this also known as keyhole surgery, is where we have the surgery is done through a very carefully controlled, I guess you could call a robotic arm, where we inflate the abdomen and we can actually perform a surgery without cutting people open. The smaller the cuts, the better. The smaller the cut, the better that's going to heal. So when my friend had his appendix removed in the 90s, he had a relatively big scar because that's how much room they needed to open up and see inside and to remove his appendix. Whereas when my friend got his appendix removed 10 years later, he only has 2 small scars, so that there's one on each side. So one is to allow you to see, and the other one's allow you to do the removing. Okay, so that's laparoscopic surgery, and we also have the insulin pump is an example of a monitor and delivery device. So when I was a kid, if you had diabetes, someone would take a blood test 2 or 3 times a day to check that their blood sugar levels were okay. and they would adjust their blood sugar by taking jelly beans if they were hypoglycemic, if they had not enough sugar. And now an insulin pump can both take the reading and give a much steadier flow of insulin than having 2 or 3 spikes of insulin throughout the day. Having a small regulated amount of insulin through the day is much better for you. Okay, so this is on, I'll mention it while I have it. So this is a course that I listened to, which I thought was very good, about the Understanding the Secrets of Human Perception, which is a really good course just to understand the how it is that we perceive things, how the optical nerve functions. So for instance, in the case of when we're talking about bionic eyes, that a bionic eye, the back of your eye, the retina, has cells. When those cells, when light hits those cells, they release a chemical charge. In the case of your eyes have 3 different three cells that receive different wavelengths. So when blue light hits, some of those cells send a signal. When green light hits, different cells will send messages. When red light hits, different cells will send messages to your brain. And when you say red and blue, it's a certain wavelength. So let's see. So in your eye, you have cones and rods, and so different cells will fire, and they'll shoot amounts of electricity depending on which wavelength. So the short wavelength, it will fire the most strongly when short wavelengths of light hit your eye, whereas the middle one, will fire when green or yellow will fire the most strongly. Probably green. When we see yellow, both the middle and long wavelengths will be activated, and so your brain will be able to decode that and say, "Oh, I'm seeing yellow." If the white light hits the back of the eye, all 3 cone cells will fire and send that electrical impulse to the brain, and your brain will be able to interpret that as white light. So that sort of stuff I learned more about through this course. Okay, so if I close that, it's going to show something else that I'm then going to want to talk about. I'm not sure what that is. So, okay, let's have a look. We've talked about what engineers do. We've talked about innovations. We've talked about artificial heart. We've talked about the bionic eye, and we've talked about artificial joints. Health and safety matters. So there is probably a greater risk for biomedical engineers than there might be in other fields, and there's certainly unique risks. So things like infectious diseases can be a risk for biomedical engineers. And another particular risk that's important is radiation. So I'm pretty sure that's this one here. Here I have a list of lost radiation sources. So for instance, in 1984 in Casablanca, someone took home, a labourer took home, a source was lost of iridium, so a radioactive isotope. They took it home and they left it in the family bedroom. 8 people died as a result of that person leaving the radioactive isotope in their room. In Brazil, a different case where it was stolen and it was left in a house. Because no one knew what it was, 250 people were contaminated. So 250 people got sick with radiation poisoning before the doctors were able to figure out, well, there must be a radiation source somewhere, and they were able to find where those people had been, and then be able to identify and find the CCM source. Okay, so we can close that one. Okay, efficiency, I know what that is. Okay, training the profession. So biomedical engineering is taught at UNSW. It's also taught at UTS, I'm pretty sure. I had a student who's, I think, taking that offer today, this year. Biomedical engineers do not need a medical degree, but there is definitely more biology that you cover in biomedical engineering than others. So in terms of career prospects, there are jobs for biomedical engineers, and I don't work in this field, so I can't say, but I do follow Reddit a fair bit, where I hear that so biomedical engineering is really a sort of an applied mechanical and electrical engineering. So, which we generally would say that a combination of those degrees is something like mechatronics, um, but but it's over a broader area, and it can be more difficult to find work. Typically, you're going, oh, okay, I'll put this on while I talk. That typically it's harder to find work straight out of uni. You probably have to do a doctorate. You have to do postgraduate work. Yeah, I would suggest it's really unlike civil engineers, where we need like thousands of civil engineers. We don't need as many biomedical engineers every year. But if you think this is your passion, if you think that this is what with the area that you really want to work in and you want to make a difference in, then there is work available. You have to be you can't be a complacent biomedical engineer. You have to really say, okay, this is going to be my passion. I'm going to pursue it actively, and you're going to have to. You may have to do more training relative to your peers to be able to find a place. Okay, relation to the community. Right at the start of the course, I talk about how very few people appreciate the effort that goes into the engineering around them. So this is as simple as if you turn off the water to your house for a couple of days, or switch off the electricity to your house for a couple of days, you very quickly start to appreciate it. But there's no one engineer that you can thank who you can shake their hands. And I think that biomedical engineering is a really good example of this, where if someone has cancer, they might thank the doctor specifically and say, thank you, you saved my life, you treated my cancer. Whereas they don't thank the nuclear engineer who developed the radioactive isotope that treated the cancer, or they don't thank the biomedical engineer who designed the radiotherapy machine that they used. And so there is a relatively good relationship with the community, but there are some points where there's contention. So this is not really a biomedical thing, but there are people. When we do telecommunications, we'll find that can be hostility for people who set up 5G towers. There's a similar attitude here, that there can be hostility for people who are rolling out or developing vaccines and other technologies. We're going to learn about cochlear implants and how they have some haters. Okay, training unique to the profession. Well, in this particular case, they're the only engineers who really study biology in any large way. There are some technologies. So we saw earlier those people commenting that it's often you need to have a pretty good understanding of both mechanical and electrical engineering, and you also have to have a fairly good understanding of fluid dynamics, which mechanical engineers do generally have a good understanding of fluid dynamics, but because there's so much to do with the pumping liquids, blood or other liquids throughout the body, you also have to usually, many of the biomedical innovations run on electricity, and they need some sort of battery source. So that's another area that some biomedical engineers need to know about. Good materials. So the biomedical engineers are more likely to use specialty materials. So we're going to learn about things like alumina, stainless steel, and titanium. And they probably have a better understanding of polymers than your average civil engineer. So ethics. Ethics is a really big section, and that I spend probably a whole lesson on, and I'm going to focus on that in a separate recording. I'm going to talk about some quick ones here, and I'll go through some details in greater length in a second. But there's an example here. They talk about the example of training with an artificial heart, but we'll leave that for a second. So, ethics. Daddy Pig, I realised Daddy Pig the other day, he's a civil engineer. He tests concrete. I should have said that in the previous video. I'm going to try and splice that in. If you've seen that now, you're like, oh, there you go. That's where that came from. Okay, so I've got some different biomedical innovations here. Okay, so this video, and it might be a couple of years old by the time you're watching this, I thought was quite a good video that outlines the field. It's already 3 years. Outlined biomedical innovation. I'm going to quickly walk through that video. I'm obviously not going to show the whole hours-long video here today. We're just going to talk about what sections they focus on. Why did that not open? Okay.
This program is classified PG. Correct?
Okay. It doesn't give me the little thumbnail. So this woman's a doctor. There was a... I probably shouldn't mention the statins drama. So we're going to see... but if I'm in class and I've got some time, remind me about catalyst and statins. So they show in the opening clip a variety of different prosthetics that people use. Here we can see a man with a prosthetic hand, and it's programmable. I don't think he has any tactile feedback, but there's pressure feedback. So he can't sense anything, but the hand can be designed to actually pick up and hold the glass without shattering. And that took a long time for robots to get that level of precision. The problem is he talks about is that these hands are very expensive, and in a country like America where people have to pay for their own, or the developing world where people have to pay for their own implants, this is a real cost. So here we can see a 3D printed hand, and I had a student who is going into year 11 as I'm recording this, who she 3D printed her own hand and used Arduino microcontrollers to control it. And I thought it was an amazing project. And so he does it in different colors. So for someone who's a fan of Iron Man, and so here we can see that that girl with her new hand. And we're seeing that this person is receiving a cochlear implant. We're going to talk about cochlear implants in a second. And then we're going to watch, what are they talking about next? So this is where we're doing brain mapping to be able to record to be able to feel sensory feedback in order to help people to pick up things or to walk and to regain their sense of touch. And I think at the end they talk about 3D printing cells at the end of this. I may have skipped over the 3D printed cells. They go through that one fairly quickly. Might be here. There we go. 3D printing and their applications for biomedical innovation. So it's worthwhile. I usually get to show that on days when I'm unwell. Okay, so, well, this is probably as good a place as anywhere to talk about cochlear implants. So this guy here, he records a video where he talks about his son and how he and his wife were deaf. And if normally in class I would show this whole video, but because I'm recording this as kind of a summary for people who are away or something like that, he's disappointed that his son is not deaf because he wanted to share the deaf community with his son. So he tried to get his son's cochlear's, the inner part of his ear removed, and he wasn't allowed to do that in the United States. But he called, well, he had to actually get someone to do the phone call for him to contact a doctor in Brazil. And then this is him going to Brazil and surgery, the removal of the cochlea. Anyway, I remember my wife showing me this video and I was pretty angry. So I'm like, I said to my wife, like, there's no way that can be legitimate, and just thinking, why would someone tell this story? And the thing that you have to remember is that sign language is a language, and the cochlear implant is leading to a world where fewer and fewer young people are learning to sign, or at least in developing countries, countries where they can afford a cochlear implant. And the point is here that there are many people who are saddened by the loss of language. So when we hear about indigenous languages, or probably the best example is the Irish language, which is it's protected by a relatively big government, and the my dad lives in Ireland, and he has had Irish neighbours, and those one of his neighbours is I'll leave this one on because it's a bit of a palate cleanser after. He had an Irish neighbour who he wanted to preserve this Irish language. He thought it was part of his heritage, and he didn't want to see it disappear. The Irish language is the official language of Ireland, and he, in his dealings with, say, to get a driver's license, my dad took him to renew his driver's license after he had it suspended because he had a vision impairment, and he had to go back home because they didn't have the form to fill out in Irish. And he's like, well, Irish is the official language of our country. You should have a form in Irish. And my dad's attitude was, but you're the one who's missing out. You're the one who's suffering by not conceding. But the problem is that in order to see change in the world, you have to suffer. You have to stand up for yourself at times when it's difficult. If you only stand up when it's easy, then you're not going to make much of an impact. He had some other examples. In class, I usually talk about some other specific examples of how this guy standing up for the Irish language, how that negatively impacted on his life. But the point is that people feel a loss when a spoken language dies, but we seem to be okay with the idea of sign language disappearing. And the deaf community has a very strong specific culture, probably as strong as, say, the Irish. Well, I don't want to say as strong as Irish culture, but it has a very active and distinct culture from the cultures of their spoken communities. And the idea that culture is going to disappear because of cochlear implants is a threat to that community. The other aspect that's worth pointing out is that cochlear implants are not perfect. You don't have perfect hearing, and they're not successful for everyone. And we see that in the Catalyst video, that it takes a lot of effort. I mean, that video there, it's, I think pretty heartwarming seeing these kids hearing for the first time. But for not everyone is this going to be a great success, and the loss of that for... So the attitude of the deaf community is that this decision has been made for children before they're old enough to have informed consent, and you should wait until they're 18 before they make this decision. And I guess that's probably I don't want to say that. I could see an argument that could be made that that's a self-serving attitude in that if they wait until they're 18, they're going to be old enough to have joined the deaf community by 18. So that's probably why that claim. That some people argue that that's why that claim is made, whereas there are many cases where parents make decisions for their children that are going to impact their life. But I guess the idea of opting that for that person to not be part of the deaf community or is a factor. So I'll close those, and we'll talk about some more ethical considerations. So. I won't go into too much detail, but I'll outline a couple more quickly. So that'll be on looking at here. Okay, so the text. Okay, so we've looked about the bionic ear and bioethics cost. So there's a question we have to ask about: how much are we willing to spend to help people? And this is a question of medicine, but biomedical engineers are so closely tied to the cost of medicine that it's worth mentioning here. So in Australia, we have a state-funded medicine, and a hip replacement can cost between $20,000 and $40,000 in Australia, and it could only have a marginal impact on the recipient. For instance, I have known people who they got a hip replacement in the last years of their life. Now, I'd like to think that the last weeks of their life. And I'd like to think that hip replacement was provided a training opportunity for someone who might not have had that experience otherwise, and we meant that a 20-year-old who needed a hip replacement got a better hip as a result of that expenditure. But that's money that was spent, and Effective Altruism, which is a charity organization, they talk about how something like $200 is about the cost it takes to statistically save one life from by preventing measles or malaria, either through mosquito nets or through vaccinations. So with that money, we could potentially have saved 100 to 200,000 lives in the developing world. So there's an ethical question to be made there about the use of that technology. Similarly, we could talk about things like MRIs and CT scans, which are very expensive technologies that if we forego the use of those technologies, we could use more X-rays in developing countries. The argument that can be made, though, is that by the widespread use of MRIs have drastically gone down in cost in my lifetime, because the more widely they're used, the cheaper they become, and the more accessible they become for the rest of the world. It's also worth mentioning, and I think this ties in nicely, the cost of medicine at the end of life. So I have a conversation with a palliative care doctor. So palliative care doctors, they are the people who treat you at the end of your life. And they talk about how perhaps the majority of the money we spend is really spent in the last years of people's lives. So if we had $100 to spend on medicine, well, $20 would go to 1% of patients. $33 goes to 2% of patients, and nearly half of all the money we spend goes to 3% of patients. Now, we understand that in the lottery of life, some people are born with medical conditions, and some people are born without. They're born healthy and without any negative medical conditions. But it is worth pointing out that generally this money is spent much closer to the end of people's lives, and there's a question of how much we are willing to spend for medical treatments. And it's something that I don't have an opinion one way or another. It's certainly not going to have an opinion on a recording, but we would perhaps be able to spend more money on people with disabilities so that they could have a better quality of life if we were willing to spend less money on people at the end of their lives. Okay, so then we're going to get to medical testing. So I think I'm caught up more or less to these pages here. So this is a journal article talking about the cost of the money we spend, need for regulation in medicine. So most people are familiar with America spending drastically more for poorer quality healthcare than we get in Australia. This is, what is this guy? He's an intensive care specialist, ICU. Doctor, specialist, I'm pretty sure he's a doctor. It doesn't say the name doctor, so maybe not. But that recording, I thought that was interesting. Okay, so animal testing. So for things like makeup, there are people who only buy cruelty-free makeup. The problem with cruelty-free makeup is that generally people the makeup that's cruelty-free has stood on the shoulders of other research that wasn't cruelty-free. That you can afford to say, oh, I know that makeup I'm buying hasn't been tested on animals because previous generations of makeup was tested on animals. The arguments can be made about testing that was done by the Nazis that was very inhumane, and whether or not we as a society, this is a Star Trek episode, where they have access to a wealth of medical knowledge, but then they learned that the medical knowledge was derived through inhumane conditions. And they have to make the decision as to whether or not they're going to benefit from that medical knowledge, or whether or not they're going to refuse it, whether or not they're going to delete the information. I will say that if you're planning on going to a field, into a career in science, you will almost certainly have to do animal testing. So you will have to take retinal bleeds, so taking a syringe to take blood from the eyes of mice, and then have to euthanize those mice at the end of it. So that's something that they don't tell you on the brochure when you go into a career in biochemistry. So Jenner was the person who developed the vaccine for smallpox, and there's a question about, well, where was that testing done? So they needed clinical trials, and in order to see that, in the case of I'm recording this in pretty much the middle of the COVID pandemic, and in order to test the vaccine is effective, there are people who have to volunteer to take that vaccine. In the case of Jenner's time, there's a lot of speculation that Jenner may have just used orphans to test his vaccine. So he gave them that vaccine and then gave them a very deadly disease, smallpox, and then recorded the results. Now, the question is that at this time it was pretty likely that smallpox was a huge problem. Smallpox has been eradicated. That means that it doesn't exist anywhere because we were able to wipe it out so completely. We were right on the verge of being able to eradicate polio, but unfortunately, in the process of vaccinating people in the Middle East, the CIA was using the data collected by the vaccinators to conduct military operations. The expression they use there is that poisoned the well, metaphorically, where now vaccines are seen as being a part of the American, I'm going to say CIA, but the intelligence gathering operations, and now there's huge opposition in the Middle East and in other countries in say North Africa to vaccinating, and so that's a consideration as well, an ethical consideration, that we want to make sure that these days we want to make sure that any attempt to eradicate disease through vaccination, that there can be no overlap between that and, say, military intelligence. Okay, so Rise for Animals, I think that page has died, but that was them. I think they had actually a pretty good summary about animal testing. And here we have use of laboratory animals in research. There's also worth mentioning that we used to do a lot of language study with gorillas and not with gorillas, with chimpanzees, because they could sign, and that's now not done anymore because we don't consider that to be humane. So that's a field of research that we just don't have access to anymore. Okay, so that's my ethics. There you go. I said I was going to do that in another video, but I think that's my main ethical considerations. I have a couple of others I might put in another video, or we'll see how we go. Okay, I have a whole bunch of just the innovations here are DNA price gouging. Yeah, I'll come back to those maybe as a bonus at the end of this video. But the point is that there's a very deep well of ethical considerations. When I ask students to write ethical considerations in their preliminary exam at the end of the year, I think I disproportionately get the Cochlear video because of I think it's such a salient, such a emotional argument. But there are a lot of other really good ones, like whether or not we should do animal testing. Okay, so the historical background. We say that there's very simple innovations from articulated limbs from the 16th century. So this is things like moving legs, and the development into polymer technology, and then into artificial joints in the 60s, artificial hearts. And then we have electrical innovations. So the cochlear implant developed in late 70s and implemented into the 80s. Blood pumps being later, and then I've talked about some modern innovations in that catalyst video. Okay, so there's a detailed study of the total artificial heart. We mentioned the polymer used is Abicor. I have looked up in the past, but I don't want to be wrong on the internet, so we'll look up what is Abicor. I'm pretty sure it's a thermosetting. Did I spell that right? Abicor, there we go. So because it's a specialty polymer, there's not going to be as much details. Yeah, okay. So I'm pretty sure it's a thermoset. We won't ask for details of the Abio core. It's a polymer. The next one is the effect of people's lives. Well, obviously, it restores their senses, which has a huge impact on just their ability to, in the case of feedback, or the bionic ear. There's also work on a bionic eye. Bionic eyes are much more difficult, but there is work towards that. And being able to restore people's senses just drastically increases the number of experiences they can have. So it improves their quality of life in their enjoyment of life. There's also something to be said about productivity. So assistive tools can allow people who would otherwise not be able to go to work to be able to be productive members of society in terms of being able to have a job and being able to contribute both in terms of economics, but also artistically, and knowing that they're having an impact on the world. That gives a lot of people satisfaction to have, to be able to create and participate in society. There's people who live longer and better quality lives, so they're free from pain. And they're less likely to spend time in hospitals. These are all benefits that we've talked about. Even prosthesis. So a friend of mine, she has an artificial eye, or not an artificial eye, she has a prosthetic eye. She has a glass eye, you might say. And just the impact of that if she didn't have access to that glass eye, I don't think it's actually a glass, but these days, but the point is that prosthetic, it's a cosmetic prosthetic. It doesn't do anything. It helps her to interact in society normally without drawing a lot of attention. She might not have been. Well, I imagine the dating scene is very different if you're wearing an eye patch to if you have a prosthetic eye that looks very, very real. With the exception that I didn't notice that she had a glass eye until we went swimming, and I noticed that her eye had water beading up, and that's where she said, actually, I have a prosthetic eye, and she could only see out of one eye. Okay, so we talked when I first started talking about CAT scanners, how CAT scanners can treat strokes without a CAT scan. We didn't know, or CT scans, it's sometimes abbreviated. It's hard to know if someone's having a stroke and whether or not we should operate on them. And so that means that people who would otherwise lose a lot of function or die are able to live their lives with minimal impact. Okay, so going through the rest of this course, let's see what we've got here. I'm going to do a quick overview and we'll have a look at what is in the rest of this course. And we're going to see that most of this stuff is stuff we've already covered. So levers. Well, levers look familiar from the very start of the course. And I had introduced at the start the 3 orders of levers. And we're going to talk about the examples of those. We've learned a little bit about mechanical advantage and its friend velocity ratio. We've said that velocity ratio is always higher than mechanical advantage because mechanical advantage is observed in reality, whereas velocity ratio, well, I like to think of it as being a virtual number. We never have a system that's 100% efficient, and so that affects that. Okay, so the efficiency is represented here by that equation. Mechanical advantage over velocity ratio gives us efficiency. That's the Greek letter eta. And I'll talk more about that in a second. So here's some examples of some levers used in biomedical innovation. So we've got a forceps, and so forceps can be used to help deliver babies. These days, I think we try to use the suction cup more than forceps, but we will use forceps when we need to. I asked around, I think last year, and I'm pretty sure they are still used. Okay, so there's this idea of the human structure and the human machine. So if you do medicine, you learn about biodynamics and the idea that you as a person can be considered to be a structure. That when you wear a backpack on only one shoulder, you're creating a bending moment in your spine. So that's why you really should balance those those moments by wearing a backpack over both arms. When you extend your arm, or when you lift weights poorly, when you use weight machines, you could be using muscles that you could actually be doing damage because it's not a natural lift, for example. So these are things that doctors and probably more biomedical engineers, they're the people who need to be most aware of the structure of the body and how those forces are displaced in the human machine. Okay, we're going to learn about forming processes. So some of this stuff we've already talked about before. What we're going to learn about is things like forging and machining, and we're going to go into casting in greater detail. So that's the focus of this topic. We're then going to look at, so this is all casting. We're then going to look at different materials. So we're going to learn about microstructures and macrostructures. And this is probably as good a place as any to talk about macrostructures. Again, Daddy Pig. I did have a window on galvanized steel, which I must have closed. So when we look at galvanized steel, it has a pattern. And that's because zinc has very large grains. It's grains that are large enough that we can see them with our eyes. Sometimes we get huge grains. These grains are probably about 5 millimeters across, but sometimes we can get enormous grains of zinc that form on the outside of galvanized steel. Whereas steel, it has much smaller grains. They're microscopic. You can't see them with your eye. So the difference between microscopic and macroscopic is whether or not we can see them with the eye. So we've learned about grain structures before, and we're going to cover that in a little bit more detail. We're going to learn about stainless steel. Now, I won't cover stainless steel in this video. I have a separate video that I've mentioned in the previous chapter where I could try and find it, but something I should have had ready, but I didn't. You might want to skip a couple of seconds if you're watching this on a video. Ferrous Metals. That's probably going to be on that one. So this is where I go through, nope, it's the teacher answers. So here we'll talk about microstructures, and we'll talk about, so we have steel alloys versus cast aluminium alloys. So that's where we talk about stainless steels in this second video. Okay, this is where we talk about efficiency. I'm going to come back to that. Okay, so stainless steel goes, and we have precipitation hardening, so that's something you need to know about. Then we have titanium alloys. Now, I set titanium as homework, and let's have a look where I've shown you. You'll most likely have a Google Doc that talks about titanium. And so what do I have here? I have titanium. I want to know about the mechanical properties of titanium. So is it hard? Is it tough? Is it elastic? Is it strong? Does it have a good UTS? Also, we're interested in things like strength to weight ratios. We want to know about the material properties. Is it dense? So that's relative to its strength to weight ratio. Is it biocompatible? So that means, does it go well on the body, or does your body treat it as a infection and try and attack it? Is it corrosion resistant? Is it magnetic? Does it conduct heat and electricity well? What crystal structure does titanium usually take? Where do we use titanium? So what are the biomedical applications? So where do we use it in biomedical engineering? Where do we use it in aviation? So what is it, the SR71? So we can see some real engineering. Titanium, the metal that made the SR71 possible. So this is a video that I may show about titanium in class. That's the catalyst video, and I have some links there to some other things. These are some of the topics that we talk about. Okay, uses. Oh, okay. So the museum. So they're in Bilbao. There's two Guggenheims. There's the Guggenheim in New York, which is the more famous one, and then there's the Guggenheim in Bilbao, and it is a massive structure, and it's built out of titanium. I will have shown, likely have shown this to you in Year 9, a video with Richard Hammond where they talk about the use of titanium as the outside cladding, mostly because it's strength to weight ratio and it's in this unusual pattern. Also, it's got good corrosion resistance. Titanium is a material that's sometimes used in bikes. And then I want you to tell me a little bit about titanium alloys. So I want you to do that as research. We talk a little bit about alloys here, but not very much. I want you to do some research individually and talk about that. Probably also talking about forming processes. We can TIG weld titanium. Okay, cobalt, chromium, molybdenum alloys. So Cyborg, who's a DC character, Cyborg, he is a software engineer. I'm supposed to include him in my list of software engineers. I read somewhere that he's a software engineer. I mean, maybe because he's got lots of computers in him. Anyway, obviously he's got lots of prosthetics, but his prosthetics are made out of a molybdenum alloy. So there you go. That's my link there. Molybdenum is an element, and we do use molybdenum where we want to. We can use it as a biocompatible material, but the problem is that we're worried about abrasion caused by using and toxicity. So that's a consideration. Okay, so polymers. We use different polymers in biomedical engineering. I'm probably not going to go back over this again when I go into more detail. We use polycarbonate. So polycarbonate is not one of the numbered ones. Polycarbonate is also used in headlights. Polycarbonate can be used in device housing. So if we need to put a internal pacemaker, we might case it in polycarbonate. We use PVC for blood bags. So PVC we don't use inside the body because it has toxicity issues, the chlorine, but we use blood bags, and a lot of containers that we use in medical applications are made out of PVC. Polyamides, which is things like Kevlar and nylon, or also known as aramids, they're used for grafts. So we also use carbon fiber for grafts. So when we need to, so if we have a skin graft, we want to take skin from one part of the body to another, or we want to use the 3D printed skin. We want to hold it in place. We might use those materials to hold it together. We use for joints. We might use very high molecular weight polyethylene. So UHMWPE. So we have lightweight. We're familiar with high density polyethylene and low density polyethylene. Well, this is really, really high, ultra high molecular weight polyethylene. We use we use it because it's got high impact resistance and it has a low coefficient of friction. We also, I don't know if we talk about carbon fiber here, but we use carbon fiber for, I mentioned grafts, but also for prosthetics. We use them for artificial legs, for instance. So sprinters, they might use an artificial leg that's made out of carbon fiber. Okay, we learned a little bit about ceramics. So we've talked about alumina before. We said that that's the ceramic used in spark plugs. We also use it for things like dental fillings. And here we have stabilized zirconium. So you might be familiar with zirconium as a cubic zirconium. It looks like diamond. So some people often talk about it as being budget diamond. I have no problem with people buying budget diamonds. I actively encourage people to buy fake diamonds because I think real diamonds are a bit of a scam. But I'll have to make sure my daughters get that message. With cracks, what happens is that we can use stabilized zirconium, and the idea is that it's an unstable crystal structure. So a way of thinking about unstable crystal structures is we could think about if you microwave a coffee cup with water, what you can get is you can get a situation that's unstable where the heat is actually hotter than what would happen if we boiled the water itself. When you boil water, when it gets over 100 degrees, the water starts to evaporate. But with a a boiled cup of coffee, it happens so quickly that the water is in an unstable state, so that when you put your when you put your spoon into the cup to stir it, suddenly that changes the unstable state, and suddenly all of that heat is released very, very quickly, and it turns to steam, and it can actually cause burns that because you can have a temperature higher than 100 degrees, and suddenly all that steam is released in one go. So this is a similar concept. The idea is that this crystal structure is unstable, but when a crack forms, so we can think of it as having there are more atoms packed into the crystal structure than you can't say it wants to achieve, but that its equilibrium would have it find. So when a crack forms, those they're actually able to relax, and they relax into the crack, and that prevents the crack from further growing. As you'll learn when you do the Year 12 course, I hate cracks. I have cracks in my apartment, and it gave me a lot of stress. And we learn about crack. There's like 4 pages on cracks in the Year 12 course, and I think it can be summarized in a very short amount of time. But in this case, stabilized zirconium can be used to fill up cracks that grow, and that stops the crack from growing, and that's a good thing. Okay, and then finally we get to part 4, and in part 4 we're going to learn about electronics, and we have already covered everything here in another recording, in the recording that's called Prelim Electronics Part 3. So I will go through it quickly at the end of this video, but there's a lot to go through here, and I don't want to waste too much time. So I don't go through the communications as part of this course, but you will likely have to write a report as part of your course. No, I make you do the breaks report. I might make you write a report on a short engineering report as just practice, so that way you're familiar when we get to the next one. Okay, so in this video I'm going to go through the levers and a few other things I said I'd come back to. So if we go through levers, we know that there are 3 orders of levers. I don't think I need the titanium thing anymore. We've talked about titanium. We have talked about that. Okay, so I have the Eureka video that covers levers, and I have no idea this is. I think this might be just the elephant. Yep, we have seen the elephant before. So what order of lever is this lever? First, second, or third? What does it look like? First order, yeah, because it looks like a seesaw. The fulcrum is in the middle. And we can see that it amplifies the force of the elephant. So, oh, there it goes. That was enough of that. We're just going to watch baby elephants. Okay. So, the first order lever is anything that looks like a seesaw. Now, this hammer, you can see, I like this example because the hammer, what we have here is that it's still a seesaw, but it's bent. So we can see that the fulcrum is somewhere between here and here, depending on the position of the hammer. And so the fulcrum, it's bent, it's at 90 degrees, but it's still the same concept. And the idea is that the fulcrum is any situation where the fulcrum is between the load and the effort. Pliers are another example, and we look at forceps. Now, typically, these will give us a mechanical advantage greater than 1. They're going to amplify our force. That's typically why we use them. However, there are examples where that isn't the case. So in the case of pliers, we might have the handle of the pliers being longer than the nose of the pliers. That amplifies force. But in forceps, we might not have that be the case. In forceps, we might have it so that the part that sticks out is longer than the handles, and as a result, that's going to give us, the reason why we do that, it's going to give us less force than we're putting in, but the reason why we would choose to do that is we choose to do that because we want precision, we want reach. So the second order lever is the wheelbarrow, and I always like to think of that as being filled up with number 2s. You know, so if you're fertilizing, you fill up your wheelbarrow with poo, number 2s.
I have to leave in about 30 minutes.
Yep. Yep. And in this case, we fill up so the load is close to the fulcrum and the effort is further away. In a third order lever, in this case, the forces are reversed, and I think of this as being like a fishing rod. I try to remember a fishing rod with 3 fish caught on the one line. The example that we look at is things like tweezers and tongs. They are often third order levers, and they give us precision rather than increase in force. So let's have a look at that in the book. That's where we cover that. You will need to be able to recognize that. So we have a mechanical advantage. Where did I have my ETA? Okay, so this is the flag of the people who want to have a Basque country. They came up with this flag. And there used to be a terrorist organization. I think 9/11 kind of ended that organization for them. That was fighting for Basque separatism, and that was called ETA. There's also the name ETA, like Etta James's singer. Anyway, we learn about efficiency in the Year 12 course, and we have some examples here of bikes. And we can see here that in this equation, what we need to find efficiency is we need to know the mechanical advantage. And then from the mechanical advantage, we can then find the velocity ratio. And once we know the velocity ratio, we can then determine the efficiency. So I have that worked out here. In order to determine the mechanical advantage, it's pretty simple. We just take the difference between the load and the effort. Or sorry, this is the load and this is the effort. Now we can see here that we get a number less than 1. Because with this bike, we're not getting an increase in power. What we're getting is we're getting bikes are incredibly efficient. So we talked right at the start of the course about how wheels are pretty good. What we want here is we're okay with having something which gives us less effort, less power than, less force than we're putting in. The power and the work are the same. I shouldn't use power, I used that incorrectly there. What we're getting is less force applied to the wheels, but we're getting a huge amount of efficiency, which means that we're not wasting much energy. That's why we like bikes. So it's important to know that bikes give us a mechanical advantage well under 1. Now the velocity ratio, that is more difficult. What we need to know here is we need to compare the distance turned by the pedal compared to the distance turned by the wheel. But we have to remember that the wheel, in this case, is going to turn around, this big wheel is going to turn around 2.5 times for every time the big wheel turns around. So if we have this as a diameter of 700, well, in actual fact, we're going to say that we can say the diameter, the distance traveled by that wheel is going to be 700 times pi times 2.5 compared to the 340 of this wheel. Now, I say this because there are questions at the end of the textbook on this, and if I'm feeling mean, I might well include a question on this. Even though it's not tested explicitly in the textbook, there's enough information that you should be able to determine this from first principles. You can say, well, if you know how far the wheel turns and you know the ratio that the wheels turn, you should be able to determine the distance traveled by the wheel to be able to determine the velocity ratio. And there's a question in the practice questions at the back of the book. Once we know those two values, we can determine efficiency, which is we use the symbol eta, by comparing the mechanical advantage to the velocity ratio. Now, in the case of this bike, it's only 80% efficient, but that's very low for a bike. Bikes are usually more efficient than that. Okay, I want to keep that open. I can keep this one open instead. Okay. I'm going to go through that in another recording. Okay, so then what we're going to go through, and we might go through this quickly, is we're going to go through forging. Now, so with forging, the idea is that if we're making, this is the stem of a hip replacement we saw earlier. If we took a blank piece of steel and then machined it to length, what we'd have is grain boundaries that would look like this. The grain boundaries would all follow the shape of the original piece of material. And so what could happen is with an impact, we might have this little part just snap off. So instead, when we forge materials, and we see forging for things like spanners, we can hot, cold, and cold forge. So forging is here. but I have some more forging here. I won't go through these videos. I'll post links that you can look at individually. About 3 minutes setup. So here we have big machines that drop into shape and forge the material. I said 3 minutes, but I don't know. For some reason I couldn't. So it's been rolled, and then we're going to see it get forged, hopefully. Here we go. That's forging. Okay, we can also have... Oh, this is a Reddit post that's just dedicated to forging. Smashing hot metal. So it's a rivet. Yeah, it's a funny old world. Okay, and so this is more like blacksmithing, but I did have a GIF of something being forged, but I can't seem to find it now. Anyway, okay, so forging, the reason why we like this is because the grain flows around the shape that we make, and that means it's going to be strong. It's not going to have a point of weakness, whereas here we can have the little tip be broken. This is an incredibly common preliminary exam question, and it's also often makes its way into forging questions, often in the HSC. Just because it's good to see actual photos. This photo, I think, has been in past HSCs. So we can see that the forging material, I have some samples that I use in my class. So if we machine, we might get a grain structure that looks like that, and that's not good. Whereas if we forge, we get that sort of grain structure. So here we have a sample that's been machined versus a sample that's been forged. And we can see the grain flow around the material. And that means that they're not going to have points of weakness. Yeah, looks like that's probably the best I'm going to get. I don't want to spend too long on this. So again, some more materials that have been forged. Okay, casting. So there is a lot on casting here, and that probably is worthy of its own video I might look at. But I will, in class, I would have shown, we have a whole bunch of ingots, which we can look at, and we can see primary pipes and secondary pipes. We learn about sand casting. Now, this is something I'll go into in a little bit more detail. I might record using the Year 12 notes, so that way you can get all of the casting in one go. But we're most interested in Year 11 course. All you need to worry about is you need to know about sand casting and investment casting. Both of these are questions I am very, very likely to put in an exam. I don't normally ask about primary and secondary pipes, but that would be a good one. Asking about grain growth, that would be good. It's worth pointing out that the numbers here are wrong. This is should be 1, and this 1, 2, 3, but you can see here it's 3. We watched a video on normalizing. I'll just quickly show you that. I watched my full video on casting, and that will go through that detail about how grain grows, grain growth. I'll then talk about the difference of what material we have on the outside. We'll talk about piping, but what I want to just quickly talk about is sand casting. So there is a guy on the internet who just does a whole bunch of casting. He has got hundreds of videos, or certainly dozens and dozens. I think he gets up to 90 videos maybe on casting. And we'll watch one of these in that recording and talk about what he's casting and how he works and using sand and those sorts of things. If I haven't in class, ask me to go on a excursion outside and we'll have a look at, there's a brass tap in B block that has been sand cast. In terms of investment casting, I'm only going to talk about this really quickly because, like I said, watch the full video. But with investment casting, the idea is very, very quickly is it's 4 steps. We make something out of plastic or usually wax. And once we make the thing out of wax, we then coat it in ceramic, which we can see here. So that's the thing being coated in ceramic. And then we fire the ceramic, which melts the wax. Oh, I missed that step. So we fill it with, yeah. So we coat the ceramic. We melt the wax out and it hardens the ceramic. We then pour the ceramic filled with metal. We then let it set. We then shake off, or we may actually physically remove with a hammer, the ceramic, and that gives us a very highly accurate cast. Now, it's worth pointing out here that with investment casting, the word investment comes from the word to surround. So it doesn't mean expensive, but that does happen to be very expensive. So it is a big cost investment as well as it coming from the word to surround. So that's where it gets its name. Okay, so fabricating, I'll cover that in the rest of the video. Crystal structures we've already talked about, microstructures we've already talked about, and then stainless steel. So all of that will be covered in greater depth in its own video on stainless steel. Just check that there's nothing else I'd said I'd cover now. Nope. And electricity, I said earlier, that's covered entirely in its own video. So that's, with the exception of casting, which is in its own video, I might make a second video where I go into a little bit more about ethics and some innovations. And I'll make another video on casting, but the casting video will cover both Year 11 and Year 12 casting. And that's it for Chapter 4. So we can see that we can cover this chapter quite quickly.